This is the example we talked about, but I didn't have time to finish. So today I'm continue to finish up this one because more importantly, when we got all those equations in different segments, we finally need to plot. So all the plots are based on the calculation you made. So that's why some students later ask me, for example, in the book, solving this problem, they use a kind of simplified way to plot the shear and moment diagram. If you look at the textbook, that's what I call the method 1, which I don't like at all because I don't think that is very applicable for all those questions. So I basically talk about a universal method, which is method 2, which you can also find from the book. That method can solve all problems. It doesn't matter when you have a concentrated load, when you have a distributed load, you can always solve the problem in a unified way. And that's the method I was introducing. I'm going to continue to use that. Okay, so I'm going to switch back to the overhead projector to finish up this example. Okay, sorry for the mess up, but I would like to quickly go over what we had last time. All right, the same example. So let's see, we have this kind of simple beam subject to 2 concentrated load acting on point A and point C respectively with a given magnitude. Finally, we need to plot the shear diagram and the moment diagram. So typically, we solve this kind of beam problem in terms of the steps. Number 1, we always need to look at the entire structure and then to plot the free body diagram for the entire structure in order to determine those reactions, because reactions are the forces applied on the beam as well. It just doesn't matter how we're going to calculate, right? So look at this one. We have this kind of beam with the 2 forces given with magnitude, but there must be another force acting on point B. We just do not know the magnitude. That's why we cut here. We plot the free body diagram with a Bx, By as the reactions from the pin, and we cut this point D as well because it's a roller. We give another force called the Dy. So this is what we call the free body diagram by collecting sigma Fx equals 0, sigma Fy equals 0, moment at a certain point, we choose point B equal to 0. We have these 3 equations. From these 3 equations, we find out Bx equal to 0, By equal to 46, dy equal to 14. That means this is 14, this is 46. Okay, so that's the first step. After we're done with the first step, calculated all the reactions, now we need to determine how many cut. What's the minimum number of cut we have to do in order to solve this problem? And the criterion is we just need to find out where we're going to encounter the discontinuity in terms of forces. So typically we want to travel from the left end always. We're starting from point A and just keep moving slowly until you see a force discontinuity at point B. Because point B is have another By all the way jump up so that there's going to be a discontinuity. So if that's the case, then AB should be our first segment. Okay? If you want to make more segments, that's not a problem. I'm talking about minimum number of segments. Okay? So minimum number of segments, that is AB first. And then we're solved with B. We continue to move slowly until you reach point C. We have to stop here because there's another force applied at point C giving us another discontinuity. Okay? So then BC is the second segment. So we have 2 segments now. And we continue to move slowly from C all the way to D until we reach the end, and there's a 3rd segment. So the minimum number of cut corresponding to the minimum number of segments is 3. So that means what? Then we need to cut 3 times. You cut more times, not a problem. But you cannot cut less than 3 times. Okay? So that's why start from second step. We need to cut based on segment AB first. Cut it in a very general way, so that after I make the cut, the whole structure is split into 2 parts. We just pick 1 part. So typically we pick the left part because there's less force involved. Now we need to replot, or we need to plot another free body diagram based on that part of the structure you pick. You pick on the left, draw the free body diagram on the left. If you want to pick on the right side, then you plot the right side. So I'm going to plot the left side. So I'm going to plot this one first. from A to somewhere. This is somewhere I call cutting point. After I make this cut, this is the location you need to identify. We cannot say this is from here to here all the way to 2.5. We cannot say it's 2.5. We cannot say it's 1. We cannot say 0.5. We need to make a general. How to make a general? We assume the distance x. So x can be equal to 0.1, can be equal to 0.5, can be equal to 1, can be finally equal to 2.5. It cannot be more than 2.5, right? Because the n is 2.5. Okay, so that's what they call x. And then you just gave all the forces acting on this part of the rigid body. So now we have a force going down with a 20. That's why I put 20 here. You cut in here. Obviously, you need to give a shear force by sign convention going down always. It doesn't matter finally the force is real going down or not. It can be going up. But before we know that, we have to make assumption. The assumption is on the left, you always assume the force is going down. And in addition, you always assume the bending moment, the internal bending moment, is counterclockwise. And that's our sign convention, which you have it in my previous slide. So this is a new free body diagram. From this new free body diagram, you're going to collect all the forces in y direction set equal 0. It's guaranteed to calculate the shear force at a cutting point. Okay? So that's why you collect all the forces, you get this one. So this is my part of the solution. We'll leave it there. And we take a moment at a cutting point. You can take a moment at any other point, it's fine. But taking a moment at a cutting point, that's easier for you. So that's why we always put the moment at a cutting point and collect the moment of all forces. Number one, we have force 20 acting on point A. So that's going to be 20 times the shorter distance. From here to here is x. And then we determine it's going to be counterclockwise or clockwise. It's going to be counterclockwise, put a positive sign. And then this moment is, by assumption, is a counterclockwise. Then it's plus moment equals 0. So finally, you get this one. So this is called the bending moment, internal bending moment, which is dependent on location, x. So if your x equal to 0, then what? The moment equals 0. If x equal to 1, that means x equal to 1. That means from here to somewhere here. No, less than this. It's total 2.5. 2.5, somewhere here, for example. If you want to know what is the internal moment at this location with from here to equal to 1, then you put x equal to 1 there, you get negative 20. That's the bending moment at that point. But this is more general because this x can be anything from 0 to 2.5. So that's why I saw the minimum cut, which is general. Okay, so we're done with the first segment. We move to the right to cut somewhere in the second segment. And that's the next step. Step number, well, I'm no longer, let me show you the next one I have. So the next one I have is to cut somewhere between B and C, right? So when I cut somewhere between B and C, well, by the way, you say, well, I already made the cut. This is gone already. If I make the second cut, do I need to look at the right side, just pick back the second, the right side and cut again? No. You need to go back to look at the original picture because the step number 2 is done. Then just leave it here. You need to go back to look at this original intact picture. This is the original picture. Every time when you make a cut, you need to go back to look at the original picture, assuming you don't cut here. Or in other words, this cut, this cut, this cut are all concurrent, not affecting each other. Okay? So going back to look at this one, I'm going to make a cut between B and C so that there's no cut here. We went back to the original picture. So we'll make this cut, then the structure fall into 2 parts again. So the structure fall into 2 parts, we just pick one. You pick the right, no problem, or you pick left. So I'm going to pick the left part. So that's why I'm starting from A again. The reason I'm emphasizing this because a student was asking later, oh, this part is gone already. Why you are still keeping this point A as a starting point? Well, we went back. We are coming back to the original picture and make the cut. It's not after we make the first cut and by sequence we're going to do the second cut. No, we come back to the original one to make another cut. Okay? Now we got the result based on the second cut, somewhere between B and C. When we make the cut, we're still starting from point A. That's very left end. So then, we're going to call x. From the cutting point to the original point A is x. You may say, well, you cannot call x because x has been used before. Well, this, again, they are all parallel. Okay? So this is x, which is different from this, in fact. Because the range, or called domain, I believe, right? Mathematics, pre-calculus. The domain of x is what? From 0 to 2.5. What is the domain of this x? The domain of this x from 2.5 to 2.5 to, no, not this one. No. 2.5 to 5.5. Okay, let me ask you again. We cut between B and C. We cut between B and C. Once we cut it between B and C, what is the domain of this x? If you say the domain of x is from 0 to 5.5, that's wrong. That means this one can be somewhere here. That's not allowed. I'm going to make a cut between B and C. So then the domain of this x should be at most at point B, that's 2.5. And from B to C, that's 3. That's why I'm called 5.5. So the domain of this x in this step is from 2.5 to 5.5. Any questions? The domain. So again, the domain of this x for this segment BC part cut is not from 0. So this x can never be equal to 0 for this case. If you want to have this x 0, go back to the previous one. The previous one, the domain of this x is from 0 to 2.5. And you're done with that one. Now you're talking about same symbol x, but the domain is different from 2.5 to 5.5. So that's why this x, in fact, is definitely different from the previous x. We just happen to use the same symbol. Any questions? Okay, so once you make this cut, again, by sign convention, you need to put the force shear going down, called V again, and then this bending moment is called M. Same thing, I use the same symbol. This is a V, this is a V. But it doesn't mean this V is the same with this. If they're always the same, you don't need to do the calculation. You just copy whatever you got in here, but that's wrong. Also, you're going to have a moment, right? So this is the bending moment. You just use the same symbol. It doesn't mean this equal to that. And then, by collecting all the force in y direction, by the way, at point B, there's a reaction. You have another force. Don't forget. So this is another force acting on point B, which is 46. You calculate it from step number 1. So by collecting all the force in y direction, you get V. So in order for each segment, after you make the cut, how to calculate the shear? You always collect the forces in y direction. This is the way to calculate the shear force. How are you going to calculate the bending moment? You need to take the moment at the cutting point and then follow the Newton's equation to get this moment. So you see, this is another moment in this step, segment BC. This is what I showed you before. Okay, so now we're done with the second segment. After make the cut, we got V equal to what? 26, and then we got a moment equal to this. Okay, so the moment is a function of x. Okay, depending on locations. Again, the domain of this x is from 2.5 to 5.5. Any questions? Yes.
Then why don't you put the x in the diagram from B?
Okay.
Yeah, that's right.
That's a good point.
That's where you're making.
The question is, sure, if you can have this x from anywhere you like. In fact, you can have this x from here, if you don't mind with more troubles, because finally, let me tell you, I'm going to plot the free body diagram. I'm going to plot the diagram, the shear moment diagram. You will see. You will appreciate if you're starting from here, it's easier for you to plot. In reality, you can definitely say, I'm defining x from B to this one, no problem. Then what's the total? That's going to be x plus 2.5, no problem. But you're going to make a little bit more trouble at the very end. I'll show you. Okay, so this is not the only way to solve problem. But if you want to make more consistent, you need to follow with a global coordinate system. So this is x, which I call the location, or you can call the variable. You can also call the coordinate system, because finally I'm going to plot x. I'm going to plot v versus x. I'm going to plot moment versus x. Or I can tell you, right? I can also switch, right? So I'll show you, okay? I'll show you, or you can remind me. Any other questions? You can solve the problem in this step, not a problem. But it's not a good idea to do that, because later on you have to switch back. Okay, so that's another segment I finished. Now I need to move to the third segment. So every time before you make the cut, you need to come back to look at the original. This is what I call the original beam. Okay, don't look at some pieces after you made the cut. So going back to look at the original, this time I'm going to cut somewhere between B and C. So after I make the cut between B and C, then the structure will split into two parts, and then you pick one part among these two. So you can obviously pick this part with more forces involved, or this time you can pick up the other part on the right. The reason this time I would like to pick this part is because I would like to have a less number of forces involved. If you are looking at this side, how many forces? 1, 2, 3. You have 3 forces. If you look at this side, how many forces? 1. I'm talking about applied forces. Okay? So let me switch to this one now. Okay, so step number 4. This time I'm going to talk about the cut at segment CD. So after I make the cut, this time I'm not considering the left side. Instead, I'm considering the right side. The right side, you need to look at from point D and to this one. So if you look at the right side, there's a sign convention you need to follow, which is the shear is going up by default or by assumption. And then the moment is clockwise by assumption, in order to be consistent with the previous effort calculating all the other shears and the moment. This is what we call the free body diagram. Now, you say, well, what's the distance? Because every time when we make the cut, we need to identify the distance using a variable. Okay? You can say, well, I would like to call this one to here is x. In fact, it's fine. But later I need to switch back. So I would like to make some consistent definition of location at the very beginning. So that's why my definition is the cutting from the cutting point always to the very left is called x. X can be different because the domains can be different. So when I make the cut from this cutting point to the very left, which is called point A, that's called x. But I'm no longer using that part. I'm using the other part. Then what is the other part? It's going to be the whole length, or called span, minus x. So you go back to look at the original picture. What is the total length from A to D? 2.5 plus 3 plus 2. 7.5. So from A to D is 7.5 meters. So then from this one, from here to here is called x. From here to this point A is called x. From A to D is 7.5. Then what is this one? That's going to be total 7.5 minus x. And that is the distance I'm going to use. So with this new free body diagram, again, in order to calculate the shear force, I need to collect all the forces in y direction. That's always the case. Okay? And then you just add all the forces, you get the shear force calculated. In order to calculate the bending moment at this cutting point, you need to collect the moment equation at the cutting point. And if that's the case, and this is the equation we can get, because for this one, you have a force applied on point D going up, 14 times the shorter distance. That's this one, which identify this. So 14 times this one is the magnitude of this moment. The reason we put the positive sign because it's going to be counterclockwise. That's why I put a positive sign. This moment itself is assumed to be clockwise. However, clockwise in any of these moment equations are treated as negative. So that's why you have to put additional negative sign in this unknown moment. And equals 0. From this equation, you can calculate the moment, which again is dependent on the location, x. For those of you who like to try out, after you make the cut, you would like to try out the left side, I guarantee you'll finally get the same thing if you do it correctly. If you do not do it correctly, of course, they're different. Any questions so far? Any questions? Okay, so we're done with our, yes?
Sorry, so when I did it using the left side, and I got that the shearing force is positive.
Well, when you look at the left side, by definition, by default, did you put the shear force going down?
No, I put it up.
Then that's wrong. By definition, you need to put the shear force going down if you look at the left side.
Why is that the definition?
because that's a sign convention. This textbook requires you to do that. Okay, if you use other books, maybe you can use the other way. But if you use the other way, then on the right, you must put this force going down. This has to be consistent. That's why I'm saying each book may have the different sign convention, which is fine. But you need to be consistent. Consistent means you need to follow the fundamental Newton's law. In this case, it's Newton's third law. What is Newton's third law talking about? Action, reaction. Okay? So the shear force you talk about on the left is the reaction, or it's the action based on another one. So if somebody hits you, then automatically the other person gets hit. That's called the action reaction. Okay? But in the opposite direction. Okay. So if you put this force going down, I guarantee to get this correct answer if you do other steps correctly. Or you can show me after class. Okay? Any other questions? Yes?
Why is it negative if it's pointing up?
Why is negative? Which one? This one?
Yes.
This is negative? Negative means this is we are following Newton's law. Again, right? Newton's first law. Okay? Collecting all the force in y direction equals 0 in order to maintain that part of the beam staying there instead of flying, right? So if that's the case, in order to satisfy this equation, this V finally end up with a negative 14. What does that mean? The magnitude of that shear force is 14. But the direction you assume here, this is your assumption, your V is assumed to be going up, right? Following the sign convention. But in reality, that shear force, in fact, is going down. Okay, because of negative sign. Any other questions?
Does that mean that all the shear is the opposite sign now, though? Because of one of them? If they're all the same, you said if you followed one up, one down, one up, one down, and if the last one is...
No, it's not. It's all consistent. Okay, when you have this beam here, at this point, if you cut it, you have two shear forces. One is on this surface, one on the other surface. So these are always in the opposite direction. Back to this one, is negative 14, right? On this one. That means you have this beam, you cut it here. So this segment, the shear force on this small part is to have the shear force going down, in fact, because negative 14. And the other one is going up. Right. When you plot, you need to follow the shear force on the left. When you plot the diagram, you need to follow the shear on the left. Yes. Any other questions? Okay. Yes.
Calculated from the left, we should end up with the negative 14.
Yes, that's right. You're right. Yes. If you do the equilibrium equation on the left, you should always end up with negative 14. Yes, always. Yeah, same thing. Any other questions? Okay, so now we are moving to the last step because we're all done. The minimum number of cuts is 3, and we're done. So just don't forget the last step, which is called the plot. So we need to finally plot, or we finally draw the shear diagram and the bending moment diagram. Okay? So let's do the final step. That's the part I did not have time last time to do it for you. So now I'm going to talk about the last part. And you need to plot. Every time when you plot, you need to give the reason. In other words, that's why you need to show all the work in the previous step. So when you plot the shear and the bending moment diagrams, what you need to do first, you need to plot this one. It's called X, always. And that's the global coordinate system. That's why, going back to that student question, why I have to define X from the very left. Because that's easier for you to plot these two diagrams. If you are setting up X from a different location, from point B or from point D, from point C, you have to switch back in the last step. That's why my suggestion is you should do it at the very beginning so that later on you don't have to readjust. Okay? Now, this is the location called X, and then the first diagram typically is showing the shear diagram. That's called the shear force V. So always starting from 0. In other words, starting from the very left. This point A, and then let me show you this picture again. Just to be consistent. Okay? So this is X. So that's why point A is here, point B is here, point C is here, point D, I probably put point D too much. That's fine. So this here. Okay? So you have point A, point B, point C, point D identified. So that's why they are consistent. Now, from A to B, there's a first segment. What is the shear force we calculated? Well, you need to go back to look at what you did. This is the shear force I calculated, which is -20. If it's -20, then you need to create a point which is called the -20. And anywhere between B and D, this shear is a constant. It's constant, then you just have to plot a horizontal line, right? Because it's constant this time. So from A all the way to B, that's a constant. And then don't forget to write down -20. And also the unit. Unit is a kilonewton, right? Kilonewton. And don't forget to write kilonewton underneath the shear. Okay? So that's the first part. And the reason I plot this one, -20, because I have my work shown before. So second segment between B and C, then you need to go back to look at your second segment. Here's your second segment between B and C. We just did it, step number 3. What's the shear force? 26 kilonewton. 26 kilonewton, then you need to, by the way, you try your best to plot on scale. Okay, 26 means in general a little bit bigger than 20, right? So that's why I'm moving up with this one, 26. Written here. And then between B and C, everywhere you have the same magnitude, shear force. That's why you plot another horizontal line as positive 26. So we're done with the second step. The last step between B and C, C and D, we need to go back to look at this step. So this step shows shear is equal to -14. If -14, then you need to move down to be 14, -14, and then you plot this one. So this, and this are the results based on the previous step. But then there's one more thing to do. You need to connect them together, okay? So that's why I have to plot the vertical line to make them connected. So this is the final answer for the shear force after following the previous 3 steps. Any questions about shear force diagram? Okay, so everything is based on our previous calculations. And I want you to show your work when you plot this. Because the question we normally ask you is, with a given beam problem, plot the shear diagram, plot the bending moment diagram. Don't just simply plot without giving us reasons. Okay, you need to show your work. Now, second, we also need to plot the bending moment diagram. So the bending moment diagram, same thing. This is called X. And then the Y direction is called the moment. And don't forget to write the unit, the kilonewton times what? Meter, right? Meter. Okay, so don't forget to write unit. If you don't write your unit here, every number you're going to write is going to end up with unit. If you write unit in here, you only need to write once. That's fine. Okay, now split into point A, point B, point C, point D. 4 points, A, B, C, D. Now we need to plot. How to plot? Going back to look at the result you got. Okay, so first of all, do you have here? No, move down. So for segment AB, this is my final, because last time I didn't have enough time to talk about with more details. This time, the bending moment is no longer constant because radius was X. Radius was X, right? It's -20X. How are you going to plot a linear function? Well, that's easy because you learned it from high school. How to plot a straight line or a linear function? You find 2 points, correct? You find 2 points. How to find 2 points? Well, this is only valid between B, A and B. That means the domain of this X is from 0 to 2.5. So the easiest way to find 1 point is to have X equal to 0. Okay? So when X equal to 0, what's that point? That's 0. Because -20 times 0 equals 0. So then I can finalize 1 point. At point A, I need to start from 0. And I'm going to give a straight line. But in order to determine going to which direction, you need to find another point. Another point of this X. You can choose anything you like. You can choose X equal to 1, that's fine. You choose X equal to 2, it's fine. You choose X equal to 2.5, that's fine. But don't choose X equal to 3, because that is beyond the domain. So X is from 0 to 2.5. So I would rather to choose X equal to another extreme, which is a 2.5. So 2.5 times X. 2.5 times 20 It's 50. So negative 50. So now that's corresponding to x 2.5 at point B. At point B, this point is negative 50. Okay? I calculated based on this equation. So now I can determine this point. Once you got 2 points, that's very easy. You just use your ruler to connect these 2 points. So this is the moment diagram in segment AB because of moment equal to negative 20x. Any questions on the first segment? Okay, so we're done with the first one. Now let's move to the second segment. That means BC part. What is the moment in BC part? You come back to look at step number 3. Step number 3, we finally end up with this. Okay, so if you look at this one, it's again a linear function. It's a linear function. If it's a linear function, we just need to find 2 points in order to plot that linear function. Okay, so this x has a domain from 2.5 to 5.5 because x equal to 2.5 corresponding to point B, x equal to 5.5 corresponding to point C. Okay, so what I'm going to do is to have first x equal to 2.5. So you punch your calculator, 26, right? 26 times x means 26 times 2.5 minus 46 times 2.5. And the answer is negative 50. Okay, so it's negative 50. You start from this point. Okay, you need to find another point. The other point, normally I would go to another extreme to have x equal to the maximum in that segment. That means x equal to 5.5. So you plug in x equal to 5.5, multiply with 26, minus 46 times 2.5. You punch your calculator, you get the result. And the result is, I have to go back to look at my solution. Positive 28. Okay, so now I need to create another point. That's probably too far, 28 actually. Okay, so I got this point corresponding to x equal to 5.5. So I get negative 50, negative 28, then somewhere in between I just plot the straight line because of linear function. I don't need to create a third point. Okay, so this is the moment distribution in segment BC. Any questions? Okay, finally I need to plot the moment distribution in segment CD. What is segment CD? We need to go back to look at the result we got. Step number 4. Step number 4, this is my moment distribution in segment CD. Again, if you look at it carefully, it's a linear function. If it's a linear function, then you need to pick 2 points. Okay? Pick which 2 points? Typically, you need to find the domain of this x. The domain of x for this one, no matter how you cut, what is the domain of this x? So that's between B and C and D. So if x equal to point C, that means domain is 5.5 from 5.5 all the way to 7.5. Okay? From here to here, 5.5, 7.5. So then, by putting x equal to 5.5, it's going to be negative 14 times 5.5 plus 14 times 7.5. And then you got a number which is positive 28. So then we got 1 point. That's this point. And the other point we need to pick is to take x equal to another extreme, which is 7.5. Put x equal to 7.5, negative 14 times 7.5 plus 14 times 7.5. That's equal to 0. So then you find out another point, which is equal to 0. So then, from these 2 points, you can plot this straight line. Okay? So this is the moment distribution in segment CD. And now you are plotting all the moment distributions for the entire range, for the entire beam. So this is called the moment diagram, and this is called the shear diagram. I'm going to switch back to my slide just to show you again the solution, this one. So, okay. So this is the moment diagram, and this is the shear diagram, okay? It doesn't matter you want to write negative 50 here or you want to write negative 50 here. The bottom line is you do need to give such number information. And it doesn't matter whether you write this point is 28 or here is 28. The bottom line, you do need to give the number somewhere. Similarly, there's a shear diagram. From these two diagrams, you'll find out something interesting. Number one, the moment does not have a discontinuity, right? If you look at the moment diagram, do we have any discontinuity? By definition, discontinuity means at a certain point, there's a jump. There's no jump, although it's switched back, but it's no jump. At this point, it's continuous, and it continues back. At this point, going up and going down, but there's no jump. So that's why, in terms of moment, there's no discontinuity, okay? Going back to look at the shear diagram, there's a lot of discontinuities, okay? Because there's jumps. Number one, from this point A, you see a jump. And the jump is what? 20. And then from this point B, you see a big jump. This is a drop, in fact, right? This is a jump. And then from point C, you see a big drop. And then at the very end, point D, you see a jump. That is very normal. Typically, when you see such jumps or drops, it is related with applied load. We come back to look at the original picture. This original picture. The reason you have this drop is because you applied a force acting at this point. So that's why, to accommodate that kind of force, that's why the shear force needs to drop. And that's exactly equal to 20, in fact. See, from here to here is 20. So that's why I have 20 here. At this point, there is a reaction, but it's going up with a 46. That's why you have to jump up 46. Here, point C, you have another applied load going down 40. So then the corresponding shear diagram has to drop 40 kilonewton. And at the very end, you have 14 support. So that's why this one going up with a 14.